All right. That last talk was awesome. I work at a software company and I spend way too much time thinking about optics, and my brain has fully melted. So we'll see how this goes. All right. We're going to talk about ASICs, so I have to start with a disclaimer. ASICs, magic, and pro wrestling are all very closely guarded secrets. Speaking publicly is a good way to have a windowless van show up, put a sack over your head, drive you down to Bay Ridge, and never be seen again. Everything I talk about, I managed to find a public reference for somewhere. So if I'm violating NDA somewhere, I'm indirectly doing it because somebody violated NDA first. That's like the legal thing, right? All of the dates I used are based on switch or chip announcements. Marketing is what marketing is, so who knows when things actually happen. And if you make chips or work for a vendor, please don't sue me. Can we just have a conversation? I like my job, and I don't have any money. And I work for a startup, so we don't have any money either. Okay, so there's a lot of folks in here. We have a pretty wide variety of skill sets. We're really going to talk for network engineers. I assume you know a little bit about hardware, a little bit about software, but really don't know, you're not experts in either. I'm not trying to speak to the ASIC designers, my friend from Nokia, who I met yesterday. I'm a software guy, please, go easy. I like to give this talk the imposter syndrome seal of approval, because I'm extremely underqualified for this. So if you have questions or comments, you can hit me up on Twitter. And if you have complaints, I don't care. So my qualifications. Why should you actually listen to me? So bad news first. I was a B- computer science student. I've never taken a physics class. True story. I'm afraid of electricity. I don't know, because I've never taken physics, I did software, I don't know anything about electricity. I failed to install a thermostat once. It was really embarrassing. And I can't spell oscilloscope, and for the keen-eyed here, you'll see that oscilloscope is spelled wrong. But there's good news. I used to work in Cisco TAC. I was escalation for routing protocols, and although you think routing protocols is just thinking about BGP all day, we also dealt a lot with the hardware. What is the performance of this router? What is the multicast replication ASIC doing? How is this MPLS label getting programmed into the ASIC? So this is really where I cut my teeth on hardware. Today I do a lot of web-scale data center design, helping customers big large-scale ASICs, large-scale networks, and then thinking about what ASICs are available in the market, what fits their need. And I also act kind of an ASIC translator at my employer. So, we look at the marketplace, we see what's out there, and we have these conversations around, does it make sense for us to invest in it? So I at least get to pretend like I know what I'm doing, even though I can't install a thermostat. So we're going to talk about a whole bunch of stuff. If you want to read the agenda, you can look at it on the PDF. So how are ASICs made? I assume it's magic. I don't really know. I'm a software guy. Let's talk about something else. So CPUs versus ASICs. This kind of sets the foundation for what we're going to talk about. An ASIC is an application-specific integrated circuit. It's a circuit built to do one thing extremely, extremely well. So I'm going to make a circuit that divides by the number 7, and it'll do it crazy fast. But it cannot divide by 6, and it cannot add 2. It can only do that one thing. Generally, any networking device that is high speed with a lot of ports is ASIC-based. There are also FPGAs, or field programmable gate arrays. It's kind of like an ASIC, but you can change it. You can push code down to it and muck with things and have it operate a little bit differently, but it's going to be a little bit slower. If you're familiar with the ASR 1000 from Cisco, that is more or less an FPGA, and the small type there is, if you disagree with me or have comments, please refer to the dumpster slide. When we're talking about ASICs and we're talking about the hardware, it's a spectrum of trade-offs. So on one side you have CPUs, and on the other side you have ASICs. And you have GPUs and FPGAs kind of in the middle. So it's a trade-off of flexibility versus speed versus cost versus power versus cooling. A whole bunch of things go into this equation. There are no 3.2 terabit CPUs because it would just start on fire. And there are no ASICs that support every single feature under the sun because it would, require the Hoover Dam to power. So compromises ends up being a core component of how you have to think about networking hardware and ASICs. Everything in that hardware is a trade-off. So again, power, space, heat, cooling, the cost to build the thing, the nanometer physics that exist out there. So let's take a real-world example. This is an older switch, but I think it highlights the point well. The Cisco Nexus 3548, their ultra-low latency switch designed for like high-frequency trading for Ethernet. 50 nanoseconds port to port, fast as hell, until you turn on layer 2. Then we jump up to 190 nanoseconds by just enabling a MAC lookup. But if you want to actually route something and build networks the right way, 250 nanos. Tiny, tiny tables. The MAC address tables, the routing tables, the ACL tables on this thing are minuscule. Because they've made the trade-offs that, look, we know where this is going to be placed. It's really designed for low latency. We're going to chuck everything off in order to make this as fast as possible. You can look at something like a buffer. So Broadcom Tomahawk, 16 meg buffer, shared buffer on the switch. So there's 16 megs of memory inside that ASIC. And you're like, cool, anybody can get 16 megs, right? But it's not fully shared. It is impossible for a port on that ASIC to get 16 megs of a buffer. And this is a little graph showing different performances based on different port speeds or traffic being injected into different ports that Broadcom's friendly competitor Mellanox put out. The great thing about having multiple vendors out in the ASIC space now is they talk trash about each other and makes for entertainment for software folks. Mellanox Spectrum, fully shared buffer, low latency. They've solved it, right? They can give you any buffer across any port. They have the lowest latency switch at 100 gig on the market. Really amazing. But you can only do 64 ports. You can't break out to more than 64 ports on that switch. They've made another trade-off. Everything is a trade-off in building an ASIC. When we think about the trade-off of time to market, everyone's getting really close. There's not a whole lot of difference in the industry anymore. Cisco has had a clear edge in ASIC design, and I say this as a Cisco competitor. I think they've clearly done a great job building ASICs over the years, but they're really losing that huge multi-year edge. At most, it's like 1 to 3 years before you see somebody like Broadcom developing more or less the exact same thing, or one of their competitors coming out with an ASIC that does relatively the same thing. So if you look at the marketplace and you say all of these ASICs out here are terrible, I hate them for some reason or another, if you just wait a little bit and just kind of like punt on your project, the next generation of ASICs is probably going to show up very soon and solve whatever problem you hate. Except for money, that one I can't solve. Everybody building these things are optimizing for different things. So the next piece, we've talked about compromises, is the pipeline. What is the pipeline? What is happening inside the ASIC? And so these ASICs have pipelines. It's a series of circuits that do stuff. So this is an example of a pipeline where you come in on the left, you go through the top part, you hit the scheduler that then sends you through the bottom to come back out the switch. And it's going to do things like L2 lookups, L3 lookups, ACLs. The pipeline determines the feature set of that ASIC. Some features literally do not exist in the ASIC and therefore can't be done. So if you've ever had the misfortune of deploying some switches and then calling support and being like, hey, I configured this stuff and nothing works. And they're like, yep, hardware limitation, can't do it. The circuits literally do not exist inside the ASIC to do the thing that you're trying to do. And then you should go kick your sales engineer in the shins for selling you the wrong thing. Pipelines can sometimes be limited to only one action. So I can either do a VXLAN decapsulation or a layer 3 lookup. I can do GRE or MPLS. I can't do both. It depends on the ASIC. I'd have to put 2 of these functions next to each other, a GRE decap and an MPLS label lookup function, or I have one function that does both purposes and you have to flip the switch for one or the other. Sometimes they solve this with what's called recirculation. and I literally just send it back through the second time. So the first time I'm going to send it through and get a GRE decapsulation, and I'm going to take that same packet out and just shove it right back through, and the second time get an MPLS lookup. Some of the Broadcom Tomahawk line of ASICs can do VXLAN routing, where they can do a VXLAN incap and an L3 lookup. They do exactly this. And whether that's through a port, a cable physically plugged into the switch with a loopback port, or it's through internal ports that are connected to each other. Some vendors have even taken the Tomahawk and basically said, this is the 40 gig version. We're going to sell it as a 10 gig switch and take all that extra bandwidth internally and just wire the chip back to itself to perform this function. So think about that. But now you're going through that pipeline twice. And so if you have a 600 nanosecond switch, well, you're going to go through that same 600 nanosecond process. So you now have a 1200 nanosecond switch for those feature sets. It's just, again, important to be aware that nothing comes for free. Next up, buffering, my favorite topic. Buffering is a religion. It's the Red Sox versus the Yankees. There's a clear winner there. It's the Red Sox. If you disagree, see slide 2. Madrid versus Barcelona, UNC versus Duke, also a clear winner there. And because I'm trying to be globally inclusive, the All Blacks versus the Les Blues, I think that's rugby. I don't understand. Depending on the ASIC form factor, depends on where the buffer lives. There's a bunch of different places you can have buffering in a switch. Is it a chassis? Does that buffer live on the line card, on the backplane, inside the ASIC? Is the buffer on chip? Is it a sidecar? Are these external bonus buffers that I'm using? And it's also really important to remember buffers mean latency. It's the act of putting a packet into storage for some period of time before I can act on it. You cannot have large buffers and low latency. It doesn't make any sense. They're not necessarily evil, but where and why matters. Again, trade-offs in building the ASIC, trade-offs in designing networks, trade-offs in picking what platforms you're going to use. So when should buffers be used, or when are they used? Primarily store and forward, right? I'm going to receive a frame in, I'm going to hold it, I'm going to do a lookup, and then send it on. Well, I got to hold it somewhere. I'm holding it in the buffer. Egress port congestion. 2 ports sending to one at the same time, right? Physics says I can only put 1 bit on the wire, so that other bit has to wait somewhere. It waits in the buffer. Especially within the data center, I tell people to think about the statistical probabilities. We get really concerned in data center about buffering and oversubscription and these kinds of things, but for most folks, you're not really going to have this problem, or it's going to be really rare and far between, and you can just retransmit. And I'm not saying that the use cases don't exist. I'm not saying that there aren't networks who need big buffers, but I think there's a lot of times where we kind of get ourselves riled up, and the reality is it's not really a big deal. Anytime the burst is larger than the pipeline speed. So the pipeline can only move packets through at a specific clock rate at some speed, and it depends on that packet size. Every ASIC is optimized for some packet size. That might be 9,000 bytes. It might be 64 bytes. And what that means is that if you're optimized for 64 bytes, and I send you 65 byte packets, I'm going to get awful performance because I'm now buffering a bunch of that traffic. Speed changes is another one. If I'm coming in at 100 gig, I have to slow down to go to 10 gig. I got to slow down somewhere. I have to have the off-ramp from the freeway. When don't buffers matter? When are we not buffering? We're not buffering in cut through, right? As a frame comes in, I'm going to immediately start sending it out. We're never going to hit the buffer. Same speeds, no congestion. 100 gig in, 100 gig out, 1-to-1 port. There's no reason for that to sit in a buffer anywhere. So the first thing of where buffers live are single chip shallow buffers. So these usually live on chip, and the buffer is part of that pipeline. Yes, it's more complicated than that, but again, see slide 2. So this is an example of the Trident 3 pipeline. Okay, packet comes in, does some stuff, and then highlighted in yellow here in the bottom right is the packet buffer. So as it's going through, it will land in the packet buffer. and it's on the chip. You know, you're not going to see any other memory if you open up the switch and look at it. It's not deep. Generally, these shallow, what we call shallow buffers, are measured in megabytes. But it also means it's usually a really high-speed switch. Because that memory is on chip, it usually can run roughly the speed of the chip. So I can write and read from that memory as fast as the switch can operate. It can also mean low latency, right? Again, buffers have speeds, but it's complicated. When we talk about buffering, you know, I just mentioned on chip, you're thinking about a single box, but we also have to think about context of a chassis. So if we look at a chassis, so something like the Arista 7300, you have an ingress and egress line card. They have some sets of forwarding ASICs. All 4 of those forwarding ASICs have buffers on them. So I have 4 16 meg buffers that are each isolated to some set of ports. I then have multiple fabric cards. Those fabric cards have a fabric ASIC. That fabric ASIC may or may not have buffers. And then I have what are called VOQ buffers. And this is true of almost every chassis, but there is a buffer on the line card called a VOQ buffer to prevent packets from going to the fabric unless there's space. So these are virtual output queues. This is how you can have a deep buffered chassis, because although each of those Broadcom Tomahawks is 16 megs, my VOQ might be multi-gig, or because I'm in marketing, I add up all of the VOQs together until you have a 36 gig buffer, even though you have a bunch of line cards with some percentage of that. And it's there to prevent fabric congestion. The idea is that the fabric is never congested, and so I'm actually going to put a packet into the VOQ buffer, ask for permission to send it across the fabric, and only when granted permission will I send it. And so the VOQ buffer is where the packet lives to prevent congestion on that backplane, on that fabric. So it's very much like a SAN, right? I have to be given a credit by the fabric, it's called an arbiter, to transmit across that fabric. And unless I'm given that credit, I'm going to live in that VOQ buffer. However, single line card can still have congestion. That VOQ buffer gets me from line card to line card. What happens if I have 2 ports on the same line card just blasting traffic? I'm never hitting that extra VOQ buffer. There are implementation details as to whether or not I am, but in general, I'm going to try to keep all that forwarding local. So I'm going to come in the first Broadcom Tomahawk and go right back out it, so I can actually exceed the buffer of that ingress line card ASIC. You know, incast to a line card can exist. I could have a single uplink and have every line card sending to that uplink, and all the back pressure is going to be pushed into the VOQ buffer, and I can still have congestion and drops there. All buffering does is buy you time. So chassis are basically leaf and spine networks. This is the Nexus 9500R from Cisco. In the green are the forwarding engines from the line cards. In the orange in the middle are their forwarding engines for the fabrics. Looks a lot like a leaf and spine network to me. You just don't know it. You don't think about it. But the takeaway from that, though, is we think of chassis being special magical devices. It's just sheet metal. I mean, there's, again, more complexity there, but, you know, don't get mixed up in the magic. So if we talk about deep buffers, there are families of ASICs with deep buffers. These are generally measured in gigabytes versus megabytes for shallow buffers. Oftentimes they are off-chip, meaning that I'm not going to put 9 gigs of memory inside the ASIC, I'm going to put it next door to the ASIC. I can have high-speed memory, but it's not that super fast L1, L2 cache like a shallow buffer ASIC. Either the physics don't exist to allow us to have that much memory and do a lookup that fast, or it's just too expensive. Again, nothing comes for free. I have to make a trade-off somewhere. The buffer can oftentimes be slower than the transmit speed. So if I have constant congestion, I can actually start to run into some real latency problems. And so if it's consistent, the buffering doesn't matter. I can still overrun any buffer under consistent congestion. And it creates extremely high latency as a result. And so here we can look at the Cisco NCS 5500. They have this huge multi-gig off-chip buffer, for however much to absorb all of these bursts. But to write to and from that memory is only 900 gigs a second. I can tell you, I don't know what it is offhand, but I can tell you that switch, or that router, is going to do way more than 900 gigs a second of total throughput and capacity. So we're again limited by our ability to read and write from that buffer if traffic gets pushed out there because we have congestion. And so the idea is that I have a little bit of congestion, I push it out there, I then can pull it back in once the congestion goes away. So that's what I mean by consistent congestion doesn't matter, because if I'm constantly filling that buffer, I'm going to have some other bigger problems. So my editorial on buffers. Deep buffers make sense for long distance transmissions. Dark fiber, the internet, basically anywhere where a tiny little burst causes a packet loss is going to crush my RTT and have pretty bad performance impact on TCP. If you hate money, deep buffers are great. It's insurance. It's not cheap. If you look at the cost per port, especially in data center switching, of a deep buffered switch versus a shallow buffered switch, it's a massive difference. Shallow buffers, basically anything else. All buffer marketing is cooked. Arista, Cisco, Mellanox, Broadcom, they all have white papers that talk about how their way of doing buffers is the best, and everybody else is stupid and doing it wrong. This is a religious debate. You can kind of do whatever you want to cook the data to make it look like you want it to. So only come with real world data, right? If you come to me and you say, look, we have this huge Ceph cluster, and when we do a big replication, we see a bunch of ingress congestion drops on our shallow buffered switch, I'm like, great, let's have a conversation about deep buffers. If you're like, sometimes I'm really worried about my Apache web server, so we probably need deeper buffers, I probably don't believe you. So briefly to talk about what are the most common ASIC families out there. Broadcom, they have the Strata SGX line. This is their data center series. It's mainly named after missiles. So Trident, Trident 2, Trident 2 Plus, Maverick, Trident 3, Trident 4. These are the feature-rich ASICs. So they're going to do things like VXLAN routing or streaming telemetry or things like that. But this is in contrast to their high-speed brothers and sisters, the Tomahawk lines, which they're going to strip out features at the sake of performance. So I think it's Tomahawk 3, for example, has no capability to do VXLAN whatsoever, but it's 400 gig. Super fast, feature poor. Strata DNX is their deep buffer line. They're named after Israeli cities. This is actually an acquisition that Broadcom did some number of years ago. You'll sometimes hear them referred to as the Dune family of chips. These are, medium to large buffers. So the ARAD, the Qumran, the Jericho, Jericho Plus, Jericho 2, Jericho 2C. These are the routing platforms you usually see out there, are the large buffered ASICs. Mellanox, they're a friendly competitor in the space. Mellanox is really focused on a single line called Spectrum, and they're trying to balance the low latency feature rich. So they're not trying to do deep buffers. They make some other trade-offs. But what I think is interesting is if we look at the timelines of ASICs, and like I said, I think that window was closing within the ASIC space. So Trident 2 was announced or came out September 2014. June of 2015, Mellanox came out with their 32 by 100 gig Spectrum ASIC. End of 2016, we had a 32 by 100 gig ASIC from Broadcom. So, they're about a year behind. Mellanox once again leapfrogs them, 32 by 200 in 2017. Qumran, the deep buffered switch, comes out. And this is interesting, right? It's 48 by 10 gig with 600 gig uplinks. But they just came out with a 32 by 100. Why are they coming out with a 48 by 10? Because it's a very feature-rich, deep buffered switch. It's focused on, edge routing, MPLS, all of those things. And so they're going to take the advantage of features and buffering at the trade-off of speeds and feeds. And you will see this consistently. Trident 3 and Tomahawk 3 both come out. Again, a great contrast. A 48 by 25 and a 32 by 400 gig switch, more or less announced at the same time. Tomahawk 3 is a race car. There's like a chair and a seat belt and a steering wheel and nothing else inside that car. Trident 3 has like 6 cup holders, like an iPad station in the back. It's the feature rich, but again, 48 by 25, a slower chip. Jericho 2 is announced 24 by 100 with 400 gig uplinks, and Trident 4 was just announced not too long ago with 32 by 400. And so I think the 2 takeaways I want you to have here are, 1, understanding that speeds versus features across the board, but also just look how fast these things are coming up. We did 48 by 10 in 2014, and here we are in 2019, we're doing 32 by 400 on a single chip. And so again, that like huge differentiation in the space that Juniper, that Cisco, and some others used to have, I think it's getting smaller and smaller and smaller. Quick note on programmable chips. So you have kind of a spectrum here. You have not programmable, which means I cannot talk to the SDK. I have no way to update a thing in software for what that ASIC does. It's a fixed pipeline. So this is what we've been talking about. What comes in on one side, comes out at the other side. There's only certain steps that can happen in the middle. You have semi-programmable. So I can't really talk to the SDK. I can't do anything, but there's a flexible pipeline. The vendor can release code and like rejigger the pipeline to do different things. The ASICs, the Cisco UDAP ASIC that they use in their Catalyst 9000 stuff is a good example of this. So, they can rejigger it and do a different thing for wireless and rejigger it and do something for Lisp, but you can't ever touch it. And then there's fully programmable. So this is like your barefoot Tofino. So it's a flexible pipeline, but you have full access. You have some programming language that allows you to tell the switch what to do and how to do it and program each step of those pipelines. And usually at a high level, the way this works is I have a bunch of forwarding engines, right? A bunch of different little mini pipelines, and I chain them all together, and I can pop out at any point in time. So as I program it, really what I'm doing is saying, okay, go to engines 1, 2, and 3, and then do these functions and then pop out. We don't need engine 4 for this. And so even that fully programmable switch is going to have some limitation of how many engines are in there, right? Again, nothing comes for free. So I put a packet in, it does each engine lookup, and it can pop out at any point that I tell it to. But let's be honest, you're not going to program an ASIC. I mean, it's great for vendors. There are a couple of folks in here that might have use cases for it, but the reality of the world is, even with something like P4, it's still super hard to do this. No one builds routing protocols. I mean, I'm a vendor that produces one of the only systems where you can build your own software on top of it, build your own routing protocol, and really go to town. And I can think of like exactly one customer that does this. So again, it's not that nobody's going to do it, but like if you're not going to do the easy software stuff, why are you going to do the hard hardware stuff? So look, there are some valid use cases. Maybe you want custom metadata. You need to understand something about that cellular packet that's coming out and hitting your mobile backhaul. I've heard some interesting use cases around trading on or forwarding based on stock ticker symbols. So I might have Exxon and Apple come in from the same exchange, and so they have the same IP group, but I want to send them to different server clusters. So I want to be able to look deeper in the packet to see what is the stock ticker in there, and then I want to send Apple over to my tech cluster and Exxon over to my commodities cluster. That's super cool for all like 30 people that need that. So, kind of in conclusion, ask some questions to your vendors, right? The goal of this talk is to arm you with enough information to start to ask questions. So the preface, and I apologize in advance for offending both VARs and SEs in the room. Your VAR probably won't know. They are integrators. They think about a lot of different vendors. They're probably not going to know this level of minutia. Again, I'm making blanket statements. There will be exceptions. Your SE might not know. Good SEs, like really good SEs might, but most SEs, this is a level of detail that they don't know, but they can go find it. So, make your vendor earn their keep. You're paying them a shitload of money. Like, make them hustle. What does that chip do well? Think about that, right? You have this chip, you have this new shiny platform coming from some vendor. What does their chip do really well? What do they think is their biggest strength? But also, what does it do poorly? What trade-off did they make, right? Is it a speeds and feeds trade-off? Is it a buffering trade-off? Is it a congestion under 65 byte packet trade-off? They made a trade-off somewhere. What is it? There was some magic function this thing does. What was it? What trade-off did they make? For that Cisco low latency switch, their trade-off was tiny tables and basically no features. So it can go super fast as long as you're not doing L2 or L3 lookups. If you ask your vendor, if I needed more speed or more features, what would the alternative be, right? Here's my specific use case, but what if I wanted to have a faster box? What ASIC would you position, and what do I lose? Well, what if I needed more features or more buffering? What would you position, and what do I gain or lose? So again, it's about thinking critically about what are we buying, what are we consuming, and how to go back to our vendors on that. Nothing is free. What is the trade-off? And that's all I've got. Thank you.